Here's something peculiar about your brain. Right now, as you sit there, part of you is running simulations of things that never happened. What if I had taken that other job? What if I had married someone else? What if I had said something different? Your mind is constantly playing this game, over and over. And here's the funny thing. You cannot make it stop. Not permanently. Why? Why does your brain insist on exploring roads you never traveled? I've watched students sit through exams, and I can see it on their faces. They're not just thinking about the problem in front of them. Part of their mind is elsewhere. What if I had studied more last night? What if I picked the other course? What if I'd gone to bed earlier? The brain just keeps churning through these alternatives, even when it's got work to do. Well, I'm going to tell you something that might surprise you. Your brain isn't broken. It's doing exactly what nature does. The universe itself is constantly asking, what if? By the end of our time together, you will understand why randomness isn't chaos. You will see why the what if question sits at the very heart of how nature works. And you might just make peace with that restless corner of your mind. Now, some of you might be thinking, Feynman, what does physics have to do with my anxious thoughts at 3 in the morning? And I would say, everything. Everything. Because the way nature computes what happens next is not so different from the way your brain computes what might have happened instead. Let me start with something simple. A coin. You flip a coin. Heads or tails. Before it lands, what is it? Now, most people say, well, it's going to be one or the other. We just don't know which. That seems reasonable, doesn't it? The coin is definitely going to be heads or definitely going to be tails. And our ignorance is just a gap in our knowledge. But is that really true? Let me push on this a little harder, because it matters. You flip the coin. Your thumb applies a force. The coin leaves your hand spinning. Now, as it rises and falls, it's rotating, tumbling. The air swirls around it, creating little turbulent eddies. The coin wobbles. Maybe there's a tiny breeze from the ventilation system. Maybe someone walked by and disturbed the air. All of these factors, theoretically, are governed by physics, Newton's laws, the equations of fluid dynamics. Nothing mysterious here. In principle, if you had a sufficiently powerful computer and sufficiently precise measurements of the initial conditions, you could predict exactly which way the coin would land. This is the position of what we call Laplacian determinism, named after the French mathematician Pierre-Simon Laplace, who imagined a vast intelligence that knew the position and momentum of every particle in the universe. Such an intelligence, Laplace argued, could predict the entire future. For such an intellect, nothing would be uncertain. The future would be as fixed as the past. Let's think about this carefully. You flip the coin. It tumbles through the air. At every instant, it's rotating, spinning, bouncing off little air currents. If you knew the exact force of your thumb, the exact angle, the exact air pressure, the exact everything, could you predict the outcome? In principle, many people would say yes. The coin is a classical object. It follows Newton's laws. Given perfect information, the future is determined. This is the clockwork universe. Wind it up, let it go, and everything that happens was always going to happen. No surprises. No real what-ifs. Just the unfolding of what was already written. For a long time, this was how we thought the world worked. And in many situations, it's a very good approximation. I can predict where a baseball will land. I can calculate when the moon will rise. I can tell you how a bridge will behave under a certain load. The clockwork picture is enormously useful. The engineering achievements of the 18th and 19th centuries were built on this foundation. Steam engines, telegraphs, railways, buildings that didn't fall down. All of it rested on the assumption that nature is predictable, that cause leads reliably to effect, that the same initial conditions always produce the same outcome. And you know what? For everyday objects, for macroscopic things, this works beautifully. You can throw a ball 1,000 times and measure its trajectory 1,000 times, and Newton's equations will match your observations to extraordinary precision. The clockwork universe is not wrong. It's just incomplete because there's a catch, a subtle catch that nobody suspected until the 20th century. But then we discovered something troubling. When we looked at very small things, at atoms and electrons and photons, the clockwork broke down. Not because we lacked information, not because our instruments were crude. The randomness appeared to be fundamental, built in, irreducible. Now, this didn't happen overnight. It took decades of experiments, decades of arguments, decades of brilliant people scratching their heads and saying, this can't be right. Consider radioactive decay. You have an atom of uranium. At some point, that atom is going to decay. It's going to spit out a particle and transform into a different element. When will it happen? Nobody knows. Not because we haven't measured carefully enough, not because there's some hidden clock inside the atom ticking down. The universe genuinely doesn't decide until it decides. The best we can do is give a probability, a half-life. In a certain amount of time, half the atoms will have decayed. But which half? That's random, truly irreducibly random. This bothered people enormously. Einstein hated this. He said famously that God does not play dice with the universe. He believed, until his dying day, that there must be some deeper clockwork underneath, some hidden mechanism we hadn't found yet. The randomness, he thought, was just our ignorance dressed up in fancy mathematics. Einstein was not a simple man, and his objections were not simple objections. He didn't just wave his hands and say it seemed wrong. He constructed brilliant thought experiments. He probed the logical structure of the theory. He pushed and prodded and tested quantum mechanics with all the intellectual power he had. And quantum mechanics survived every time, every single time. But here's the thing. Every experiment we've ever done suggests Einstein was wrong about this particular point. Not wrong about relativity, not wrong about the photoelectric effect, but wrong about the dice. Nature really does seem to play dice, and she's very good at it. Now wait, let me be careful here. I don't want you to misunderstand. When I say nature plays dice, I don't mean anything goes. The dice are loaded, you see, loaded in very specific ways. The rules about how the dice are loaded, that's what we call the laws of physics. Nature isn't random in the sense of being chaotic or unpredictable. She's random in the sense of being genuinely open to multiple possibilities. Let me give you a picture of this. Imagine a drunk man leaving a bar. He's standing at a lamppost, and he needs to get home. But he's so drunk that each step he takes is random. He might step forward, he might step backward. Each step has nothing to do with the step before. He's not heading anywhere in particular. Let me be more precise. At each moment, our drunk friend flips a mental coin. Heads, he steps right. Tails, he steps left. One step at a time. Each step is independent. The coin has no memory. It doesn't know what happened before. It doesn't care where the drunk wants to go. Now, you might think this poor fellow will never get anywhere. After 100 steps, where will he be? Here's the beautiful thing. On average, he'll be right back where he started. The expected position is 0. Forward and backward cancel out. If you took 1,000 drunk men, all starting at the same lamppost, all flipping their mental coins independently, and you average their positions after 100 steps, the average would be 0. Half of them would be to the right, half to the left, and it all balances out. But if you ask a different question, if you ask how far from the lamppost he's likely to be, the answer is not 0. Even though positive and negative steps cancel on average, the distance grows. After n steps, he's typically moved a distance proportional to the square root of n. Not n squared. The square root of n. Let me say that again, because it's important. The average position is 0, but the average distance from the starting point is proportional to the square root of the number of steps. This is remarkable. It means that random motion still gets you somewhere, just not very efficiently. 100 random steps get you about 10 steps away from where you started. 1,000 random steps get you about 30 steps away. The wandering adds up, but slowly. Think about what this means. If you wanted to get 100 steps away from the lamppost, and you could walk in a straight line, it would take you 100 steps. But if you're walking randomly, it takes you 10,000 steps on average. Random walking is about 100 times less efficient than directed walking for that particular distance. Now, here's something even more interesting. In one dimension, on a straight line, The drunk will eventually return to the lamppost. Given enough time, he'll stumble back to where he started. This is guaranteed. Probability 1. In 2 dimensions, on a flat plane, the same is true. The drunk, walking randomly on a sidewalk grid, will eventually return home. It might take a long time, but it will happen. But in 3 dimensions, flying through space, the drunk will probably never return. He'll wander off into infinity, never coming back. Isn't that strange? The number of dimensions changes whether randomness brings you home. This drunk walk, this random walk as we call it, turns out to be everywhere in nature. The motion of smoke particles in air, the diffusion of perfume across a room, the way heat spreads through a metal, the way prices fluctuate in a market, the way genes drift through a population. Random walks are one of the most fundamental patterns in all of physics, in all of science. And here's where it gets interesting for our what-if brains. When you think about the past and wonder what if, you are essentially running your life backward through a kind of random walk analysis. You're asking, of all the paths that could have led to where I am now, which ones were more likely, which ones were less likely, what tiny nudges might have sent me down a completely different trajectory? Your brain is doing probability theory. Not formally, of course, but intuitively. It's exploring the space of possible histories. Now, let me tell you about something stranger, much stranger. When we look at the very small at quantum mechanics, we find that nature doesn't just explore possible histories after the fact. She explores them before they happen, all of them, simultaneously. I want you to clear your mind for a moment and really try to follow this, because it's one of the most remarkable features of the quantum world. Let me set up a thought experiment. You have a particle, let's say a photon, particle of light. You're going to send it from point A to point B. In the classical picture, the photon travels in a straight line, takes the shortest path, nice and simple. That's what light does. It takes the fastest route. This is Fermat's principle, and it's been known for centuries. But in quantum mechanics, something peculiar happens. The photon doesn't take a single path. It takes every path. It goes in straight lines, yes, but it also goes via curved detours. It goes via Tokyo. It goes via the Andromeda galaxy. It bounces off the walls. It loops around. Every conceivable route from A to B is explored. Now, you might say, that's absurd. How can it take every path? And I would tell you, I agree, it sounds absurd. But that's what the mathematics says, and the mathematics agrees with every experiment we've ever done. Let me be a little more precise, because I don't want you to think I'm just making things up. The way it works is this. Each path contributes something called an amplitude. It's a number with a direction, like a little arrow. You can picture it as a tiny clock hand pointing in some direction. As the photon travels along a path, this little clock hand rotates. The rate of rotation depends on the energy and momentum of the photon. Now, when you add up all the arrows from all the possible paths, most of them cancel out. The arrows point in different directions and they neutralize each other. If one arrow points up and another points down, they add up to nothing. If one points left and one points right, they cancel. But the arrows from paths that are close to the classical straight line, those arrows tend to point in roughly the same direction. They add up, they reinforce. Why? Because paths that are near each other in space and time have clock hands that rotate at similar rates. They stay in sync. They point the same way. And when you add them up, you get a big arrow. Paths that are far from the classical path, the crazy paths that visit other galaxies, their clock hands rotate wildly. They get completely out of sync with each other. They point in every direction. And when you add them all up, they cancel to nothing. So the net effect is that the photon behaves as if it mostly travels the straight line path, but that behavior emerges from exploring every possible path and having them interfere with each other. This is the path integral, the sum over histories. I spent a lot of time working on this formulation because I found it beautiful. It tells you that the way nature works is to consider every possibility and then add them up with appropriate weights to get the final answer. Let me give you an analogy that might help. Imagine you're trying to find the lowest point in a valley. One way is to do calculus. Find where the derivative is zero. Solve the equations. But another way is this. Release water everywhere, simultaneously, and see where it collects. The water finds the lowest point not by calculation, but by exploring all possibilities and letting them average out. Quantum mechanics is a bit like that. Nature doesn't calculate the optimal path and then send the particle along it. Nature explores all paths simultaneously and lets them interfere. The optimal path emerges from the interference. Your what-if brain is doing something similar. It's exploring alternative histories. And even though most of those alternatives cancel out, they still contribute to how you think about the present. They shape your understanding of what matters, what was lucky, what was earned. But let me give you a more concrete example. The double-slit experiment. This is my favorite experiment in all of physics. I've said before that it contains the only mystery of quantum mechanics. Everything else is just elaboration. You have a wall with two narrow slits in it. You shoot particles at the wall, one at a time. Behind the wall is a screen that records where each particle lands. Now, if particles are like little bullets, you'd expect to see two bright bands on the screen, one behind each slit. That's what you'd get if you threw baseballs through two doors. The baseballs would go through one door or the other, and you'd see two piles of baseballs on the other side. Makes sense. But that's not what happens with electrons. That's not what happens with photons. Instead, you get a pattern of bright and dark bands across the whole screen. An interference pattern. The kind of pattern you'd get from waves going through two holes and overlapping, like ripples in a pond. If you've seen ripples from two stones dropped in a pond, you know what I mean. Where a crest meets a crest, the water goes up extra high. Where a crest meets a trough, they cancel out and the water stays flat. You get a pattern of ridges and flat spots. That's exactly what we see on the screen with electrons. Ridges and flat spots. Bright bands and dark bands. Here's the thing that's truly strange. You can send the particles through one at a time. One particle, wait a while. Another particle, wait a while. Each particle goes through the apparatus alone. There's nothing to interfere with. Let me emphasize this. We're not sending a beam of particles. We're sending them one at a time. Each electron is a solitary traveler. It has the whole apparatus to itself. And yet, over time, the same interference pattern builds up, dot by dot. Each electron lands somewhere on the screen. If you collect enough dots, they form the pattern. The pattern that looks like wave interference. Each individual particle, going through alone, somehow knows about both slits. It's as if each particle explores both paths, even though there's only one particle. And when you add up the contributions from both paths, you get interference. But wait, can we check which slit the particle went through? Can we watch it? Yes, we can. We can put a detector near the slits to see which way the particle goes. We can set up a little sensor that tells us this one went through the left slit, or that one went through the right slit. And when we do that, the interference pattern disappears. We get the two bands pattern, the classical pattern, the pattern you'd expect from little bullets. Let me say that again, because it's crucial. If we don't look, we get wave interference. If we look, we get particle behavior. The act of looking, of gathering information about which path was taken, destroys the interference. This is deeply strange. It's as if the universe maintains a kind of uncertainty, a kind of openness about which path was taken, and that openness is necessary for the interference to occur. When you force a definite answer to the what-if question, when you demand to know which path it really took, the multiplicity of possibilities collapses into a single history. Let me dwell on this for a moment, because it's one of the deepest puzzles in all of physics. As long as the path is not determined, as long as we cannot say which slit the particle went through, the particle behaves as if it went through both. The possibilities coexist. They interfere. They produce the wave pattern. But the moment we obtain information about the path, even in principle, even if we don't actually look at the detector's readout, the interference vanishes. The wave pattern becomes a particle pattern. It's not that the act of observing physically disturbs the particle. Well, it might do that too, but that's not the essential point. The essential point is about information, about correlation with the environment. Now, I want to be very careful here about what this does and doesn't mean. There's a common misconception that consciousness somehow affects quantum mechanics, that the observer's mind is doing something magical. You'll hear people say things like, consciousness collapses the wave function. You'll hear that quantum mechanics proves we live in a mind-dependent reality. I don't believe that. The mathematics doesn't require that. What it requires is interaction, measurement, correlation with the environment. The looking can be done by a machine. It can be done by a Geiger counter that clicks when a particle passes. It can be done by a photographic plate. It can be done by any physical system that records information. In fact, it can be done by a rock if the rock happens to be in the right place to scatter the particle differently depending on which path it took. The rock doesn't have consciousness. The rock doesn't know anything. But if the rock's state becomes correlated with the particle's path, that's enough. The interference is destroyed. The point is not that consciousness is special. The point is that information is special. The universe seems to keep its options open as long as no record is made of which option was taken. Once a record exists anywhere, the multiplicity collapses. This is related to a phenomenon called decoherence. When a quantum system interacts with its environment, with the air molecules, with the photons bouncing around, with everything else, the environment becomes entangled with the system. Information about the system state leaks out into the environment. And once that information is out there, spread across billions of air molecules, the quantum interference is effectively destroyed. The environment measures you, whether you like it or not. This should make you think about your own what-if reasoning. When you imagine an alternative past, you're imagining a history that was never recorded, a path that was never observed. In some sense, you're touching the quantum ghost of possibility space, the realm of might-have-beens that still whispers into the present. Now, I want to address a misconception that people sometimes have about randomness. They think that if something is random, it's unknowable, unpredictable, useless, a counsel of despair. That's completely wrong. Let me tell you about a man named Blaise Pascal. He was a French mathematician in the 17th century, and he got interested in gambling. Specifically, he wanted to understand how to divide the stakes in a game of chance that gets interrupted before it's finished. This might sound like a trivial problem, but it led to the birth of probability theory. Pascal and his colleague Pierre de Fermat, working together through letters, developed the mathematical framework for analyzing random events. And what they found was that randomness has structure, deep, beautiful structure. Consider a simple example. You flip a fair coin 10 times. What's the probability of getting exactly 5 heads? You might think, well, half should be heads, so 5 heads out of 10 flips should be very likely. But that's not quite right. The probability of exactly 5 heads is only about 25%. Most of the time, you'll get 4 or 6 or some other number. But here's the thing. We can calculate that 25% precisely. We can predict exactly how random sequences will distribute themselves. We can't predict any individual flip, but we can predict the statistical pattern with perfect accuracy. The whole field of probability theory is about finding the patterns in randomness. Statistics is about extracting signal from noise. Thermodynamics is about what happens when you have so many random pieces that their collective behavior becomes perfectly predictable. Take a gas in a box. Each molecule is bouncing around randomly, colliding with other molecules, changing direction unpredictably. Any individual molecule is essentially impossible to track. Its path is hopelessly complicated. It collides billions of times per second, each collision sending it off in a new direction. But the gas as a whole has a definite temperature, a definite pressure, a definite volume. These macroscopic properties emerge from the chaos of microscopic randomness. And we can measure them, we can predict them. We can use them to design engines and refrigerators and rockets. This is one of the most important ideas in physics. Microscopic randomness can produce macroscopic order. The more particles you have, the more predictable the collective behavior becomes. Here's a way to think about it. If you flip one coin, you might get heads or tails, very uncertain. If you flip 100 coins, you're overwhelmingly likely to get between about 40 and 60 heads. That's still some uncertainty, but much less. If you flip 1,000,000 coins, you're virtually certain to get between about 499,000 and 501,000 heads. The percentage deviation from 50% gets smaller and smaller as you flip more coins. So randomness at the individual level produces regularity at the aggregate level. This is why insurance companies can make money even though they have no idea which particular person will get into an accident. They know the statistics, and the statistics are stable. Now, here's something that connects back to your what-if brain. Why does thinking about alternatives feel meaningful? Why isn't it just idle speculation? I've thought about this a lot, and I think it's because your brain is a statistical engine. It's trying to build a model of the world, and a good model isn't just about what happened. It's about the entire space of what could happen. Understanding the alternatives helps you understand the contingencies, the fragilities, the robust features of your situation. Think about it this way. If you got a job and you think, what if I hadn't gotten this job? You're really asking several questions at once. How much of my success depended on luck? How much depended on my choices? What should I be grateful for? What can I take credit for? How fragile was this outcome? Could it easily have gone the other way? What does this tell me about future situations that might be similar? These aren't idle questions. They shape how you plan for the future. They shape how you relate to other people. They shape how you understand yourself. A person who thinks they succeeded entirely through their own merits, with no element of luck, will behave very differently from a person who recognizes the role of chance. The first person might be arrogant, unsympathetic to those who failed, and unprepared for setbacks. The second person might be humble, compassionate, and adaptive. Both people experience the same events, but their understanding of the space of alternatives is completely different. And that understanding shapes their character, their decisions, their lives. Here's another way to think about it. A person who never considers alternatives is like a physicist who only knows the one path a particle actually took. They're missing the interference pattern. They're missing the structure that explains why things turned out the way they did. In quantum mechanics, the actual outcome only makes sense in the context of all the outcomes that didn't happen. The probability of finding the particle here, at this spot, depends on all the paths that could have led here and how they interfere with each other. Your life might be the same way. The meaning of what happened to you depends on what didn't happen. The significance of your choices depends on the alternatives you didn't choose. You can't fully understand your history without understanding the branching tree of possibilities that it emerged from. Let me tell you about something that confused me for a while. It has to do with the direction of time. The laws of physics at the microscopic level are mostly symmetric in time. If you took a movie of two particles colliding and bouncing off each other, and you ran the movie backward, it would look perfectly normal. It would obey the same laws. Take Newton's equations. They don't care which way time flows. Given the positions and velocities of all particles at any moment, you can run the equations forward to predict the future or backward to reconstruct the past. The mathematics is identical in both directions. The same is true of quantum mechanics. The fundamental equation, Schrödinger's equation, is time symmetric. It describes how quantum states evolve, and it works just as well backward as forward. But our macroscopic world doesn't work like that. Eggs break but don't unbreak. Coffee cools but doesn't uncool. We remember the past but not the future. Time has a direction. Where does this direction come from? This puzzled physicists for a long time. If the fundamental laws don't distinguish past from future, why does the world look so different in the two directions? The answer has to do with probability, with randomness, with the fact that there are many more ways for things to be disordered than ordered. Let me give you a concrete example. An egg can break into millions of different arrangements of yolk and shell, fragments everywhere, splattered on the floor in countless patterns. But all those broken eggs came from basically one configuration, the intact egg. There's essentially one way for an egg to be whole and a staggering number of ways for it to be broken. Going from one state to many states is easy. It happens naturally. It's just what probability predicts. If you start with a rare, special state and let random things happen, you'll end up in a common generic state. That's just the law of large numbers. Going from many states to one state requires a miraculous coordination of all the pieces. Every fragment would have to be moving in exactly the right direction at exactly the right speed to reassemble into a pristine egg. It's not forbidden by the laws of physics, but it's astronomically unlikely. It's not that the backward process is impossible, it's that it's astronomically unlikely. If you waited long enough, vastly longer than the age of the universe, random fluctuations might reassemble an egg, but you're not going to see it happen. The odds are something like 1 in a number with more zeros than there are atoms in the observable universe. So the arrow of time, the reason your what-ifs only go backward and not forward, is because of probability. The past is the one thing that happened. The future is the many things that could happen. Your brain, in asking what if, is exploring the tree of possibilities, but only the branch that was already traversed. Actually, let me be more careful here. You do ask what if about the future. You imagine possible scenarios, you plan, you worry, but there's an asymmetry. When you think about the future, you're thinking about genuine possibilities that haven't been determined yet. When you think about the past, you're thinking about possibilities that were real once but are now closed off. The regret you feel about past what-ifs is different from the anxiety you feel about future what-ifs. And that difference tracks the asymmetry of time itself. Now, I want to say something about Einstein's discomfort with quantum randomness. Einstein wasn't stupid. He understood the experiments. He understood the mathematics. His objection was philosophical, not technical. He believed that the universe should have a complete description at all times, that the randomness we see should be traceable to some underlying variables we haven't discovered yet. This is a respectable position. People have worked very hard to find such hidden variable theories, and some versions can reproduce some of the quantum predictions. Einstein's idea was this: maybe each particle has some internal property that determines what it will do when measured. We don't know this property, we can't measure it directly, but it's there, sitting inside the particle like a hidden instruction manual. The apparent randomness is just our ignorance of these hidden instructions. This would be wonderful if true. It would restore determinism. It would make the universe clockwork again, just with some gears we can't see. But here's the thing. In the 1960s, a physicist named John Bell showed that any hidden variable theory that tries to preserve Einstein's intuitions must have a very strange property. It must be non-local. Information must travel faster than light, at least behind the scenes. Let me explain what Bell found. He considered a situation where two particles are created together in a special correlated state. They fly off in opposite directions. Far apart, experimenters measure them. In quantum mechanics, the outcomes of these measurements are correlated in a peculiar way. If one experimenter gets a certain result, the other experimenter is more likely to get a related result, even though there's no way for information to travel between them in time. Bell showed that there are limits to how strong these correlations can be if the particles are carrying hidden instructions set when they were created. The correlations can't be too strong. They obey certain inequalities. But quantum mechanics predicts that these inequalities can be violated. The correlations can be stronger than any hidden variable theory allows. Experiments have been done over and over with increasing precision, with fewer and fewer loopholes. They consistently support quantum mechanics and violate the limits that local hidden variables would impose. So if you want to keep Einstein's dream of underlying determinism, you have to give up something else he held dear, the idea that influences can't propagate faster than light. You can have hidden variables, but they have to be non-local. They have to involve instant coordination across arbitrary distances. Most physicists have concluded that it's simpler to just accept the randomness as fundamental. The universe, at its deepest level, really does explore multiple possibilities. The what-ifs are built into the fabric of reality. Now, I should say that this is still an area of active research and debate. There are interpretations of quantum mechanics that try to restore some form of determinism. The many worlds interpretation, for example, says that all possibilities happen in different branches of a splitting universe. That's deterministic in a sense, but it's a strange kind of determinism where every version of you experiences every possible outcome. There are also pilot wave theories developed by David Bohm and others that restore determinism at the cost of non-locality. The particles have definite positions at all times, guided by a pilot wave that instantly coordinates their behavior across space. These are interesting ideas, and I don't want to dismiss them, but they all have strange features. They all give up something that seems intuitive. The choice is not between quantum weirdness and comfortable classical physics. It's between different kinds of weirdness. My own view? I've learned to accept the uncertainty, to find beauty in it, to see it as a feature of nature, not a defect. The world is richer than we imagined, more open, more full of possibilities. That's not a tragedy. That's a wonder. Now, I don't want you to go away thinking that quantum mechanics is mystical or that it means anything goes. The rules are very precise. The mathematics is rigorous. The predictions are exquisitely accurate. Quantum mechanics is arguably the most successful scientific theory ever devised. It underlies the transistors in your radio, the chemistry in your body, the structure of stars. The randomness is real, but it's constrained. It's lawful randomness. Probabilistic certainty, if you like. Let me give you an analogy. You know how a die works. You roll a fair die, and each face has a 1 in 6 chance of coming up. The outcome of any individual roll is uncertain, but the statistics of many rolls are completely predictable. Quantum mechanics is like that, except the dice have infinitely many faces, and the probabilities can interfere with each other in complicated ways. But the rules for computing the probabilities are fixed. There's no ambiguity. Given the setup, you can calculate exactly what the odds are. So nature plays dice, but she always uses the same dice, thrown according to the same rules. That's not chaos. That's a different kind of order. Now, let me talk about why this matters to you personally. You are made of atoms, quantum atoms. Every chemical reaction in your body, every electrical impulse in your brain, every photon that enters your eye is governed by quantum mechanics. The randomness is there, percolating through your biology. Does that mean your thoughts are random? Does that mean your choices are just quantum fluctuations? I don't think so. Not in any simple way. The brain is a warm, wet system with billions of neurons. Most quantum effects average out at that scale. The decisions you make are not typically balanced on a single quantum event like Schrödinger's cat. But the philosophical point remains. You exist in a universe where genuine novelty is possible, where the future is not simply a readout of the past, where the space of possibility is vast and real. Your what-if brain is attuned to this. It's constantly probing the space of alternatives, trying to understand the structure of possibility, trying to navigate a world where things could go many different ways. This is a feature, not a bug. Let me tell you what I think the what-if function is good for. First, it helps you learn. When you consider how things could have been different, you're doing counterfactual reasoning. You're asking, what was the cause? What was the crucial factor? This is the same kind of reasoning that scientists use. We don't just observe what happened. We try to understand which variables mattered. Think about how we do experiments. We change one variable while holding others constant. We compare what happened with what would have happened if we'd made a different choice. That's counterfactual reasoning. That's what-if thinking applied systematically. When you replay a conversation in your head and think, what if I had said something different? You're doing the same thing. You're trying to identify the causal structure. You're trying to figure out which of your words mattered and which didn't. This is valuable. This is how you improve. Second, it helps you prepare. By imagining alternatives, you build a more robust model of the world. You can anticipate threats, plan for contingencies, recognize opportunities. A mind that only knows one history is brittle. A mind that knows many possible histories is flexible. Consider a chess player. A good chess player doesn't just think about the moves they're going to make. They think about the moves their opponent might make. They explore branches of the game tree. They consider alternatives. The more alternatives they can evaluate, the better their decisions. Your what-if brain is doing the same thing for life. It's exploring the game tree. It's mapping out the space of possibilities. And that map helps you navigate. Third, it keeps you humble. When you realize how much of your life depended on factors beyond your control, on lucky breaks and random chances, you become less arrogant about your successes and less harsh about others' failures. You appreciate the role of fortune. I think this is extremely important for being a decent human being. We tend to attribute our successes to our own virtues and our failures to bad luck. We do the opposite for other people. We attribute their successes to luck and their failures to their defects. This is backwards, or rather, it's biased. The truth is that luck plays an enormous role for everyone. What if thinking can help you see that? It can make you more compassionate. But there's a danger too. The what if engine can run out of control. You can get stuck in loops, replaying the same scenarios, torturing yourself with regrets, imagining disasters that never happened and never will. I've seen students do this. I've done it myself. You make a mistake, and then you replay it over and over in your mind. What if I hadn't done that? What if I had been smarter, faster, better? The scenarios keep multiplying. The regret keeps growing. And none of it changes anything. This is not productive thinking. It's mental noise. It's the engine spinning without engaging the gears. There's a difference between exploring alternatives to learn from them and exploring alternatives to punish yourself. The first is useful. The second is just suffering. The key is to use what if as a tool, not to be used by it, to recognize when you're extracting genuine insight and when you're just generating anxiety, to know when to let the alternatives go and focus on the actual path you're on. How do you tell the difference? I think it comes down to action. If your what-if thinking leads you to do something different in the future, it's productive. If it just makes you feel bad about the past without changing anything, it's not. And sometimes you have to accept that you can't change anything. The past is fixed, the record is made, the interference pattern has collapsed into a single history. You can analyze it, you can learn from it, but you can't undo it. Nature, after all, doesn't dwell on her abandoned possibilities. Once the particle lands on the screen, the interference pattern doesn't matter anymore. The fact is recorded. The history is fixed. The universe moves on, and so should you. I want to say one more thing about doubt. I've spent my whole life not knowing things. I have approximate answers, possible beliefs, different degrees of certainty about different things, but I'm not absolutely sure of anything. And I think that's wonderful. I think it's much more interesting to live not knowing than to have answers that might be wrong. The uncertainty keeps you honest. It keeps you looking. It keeps you asking questions. People sometimes ask me, doesn't it bother you not to know the answers? Doesn't it make you anxious? And I tell them, no, it doesn't frighten me. Being lost in a mysterious universe without any purpose, which is the way it really is as far as I can tell, doesn't frighten me. The not knowing is part of the adventure. Think about it. If we knew everything, what would be left to discover? The pleasure is in the finding out. The pleasure is in the uncertainty being resolved, bit by bit, through effort and ingenuity. If the answers were just given to us, we'd have nothing to do. That's what science is. It's not a collection of facts. It's a method of doubt, a way of asking what if about the universe and checking the answers. Your brain does this naturally. It doubts, it questions, it imagines alternatives. The trick is to harness that impulse productively, to turn the endless what-ifs into experiments, into tests, into knowledge. And when you can't test them, when the alternatives are lost to history, to let them go, to make peace with uncertainty, to find the interference pattern of your actual life and appreciate its strange, improbable beauty. But here's one more thought, and I want you to sit with this one. I said earlier that the path integral considers all possible paths and adds them up, even the crazy paths, even the paths that visit the Andromeda Galaxy on the way from your porch to your mailbox. In some sense, all those paths contribute. Even though their contributions mostly cancel, the straight-line path is not separate from the rest. It emerges from the rest. It's the constructive interference of paths that are nearby in configuration space. Maybe your life is like that. Maybe the life you've lived isn't separate from the lives you could have lived. Maybe it's the constructive interference of all the choices, all the chances, all the possibilities that happen to reinforce each other in just the right way. And maybe that's why you keep asking, what if? Not because you want to escape your life, but because you dimly sense that your life is a pattern in the space of all lives. A wave made of many overlapping waves. A history emerging from the sum of all histories. I find that a beautiful thought. Now, I've been talking for a while, and I want to leave you with something to think about. Here's a question. If the universe really does explore all possibilities at the quantum level, if every alternative has some kind of reality in the mathematics, what does that mean for you? Some people find this disturbing. They want their choices to matter. They want their lives to be unique. I don't see the contradiction. Your choices do matter. They determine which interference pattern you contribute to. Your life is unique, the particular sum of amplitudes that led to you, here, now, thinking these thoughts. But you're not alone in possibility space. You're part of a vast tapestry of what might be. And that tapestry has a structure, a beauty, a mathematical coherence that we're just beginning to understand. When you ask, what if? You're touching that tapestry. You're doing what nature does, exploring the alternatives, feeling for the pattern. Some people ask me, does this mean we should give up looking for explanations? If things are fundamentally random, what's the point of science? I think that gets it exactly backward. The randomness isn't an obstacle to understanding. It's part of what there is to understand. The patterns in the randomness, the structure of the probabilities, the rules of the dice, these are the deepest laws of nature. Finding those rules is the whole point. We don't throw up our hands because the weather is unpredictable. We develop weather forecasting. We learn the statistics. We understand the probabilities. The same with quantum mechanics, the same with everything. Uncertainty is not the end of knowledge. It's the beginning. Because to understand uncertainty is to understand the structure of what's possible, and what's possible is far richer than what actually happens. Let me leave you with a story. When I was a young man, I worked on the atomic bomb at Los Alamos. It was the most intense period of my life. We were trying to do the impossible, build a device that no one was sure would work, and we were doing it in a race against time. There were moments when I wondered, what if we don't succeed? What if the Germans get there first? What if this whole thing is a mistake? The what-ifs were constantly buzzing around. But you know what got us through? We didn't dwell on the alternatives. We focused on the problem in front of us. We calculated. We experimented. We checked our answers. We did the work. The what-ifs were useful for motivation, for caution, for planning, but they weren't useful for paralyzing ourselves with worry. When you've got a job to do, you do the job. The universe will decide the outcome. Your role is to give it your best shot. That's what I've tried to do my whole life. Not to have all the answers, but to engage with the questions, to be curious, to doubt, to explore, and then to move on. So the next time your brain won't stop asking, what if? Remember this, you're not broken. You're doing physics. The universe plays dice, and you're one of the dice. Roll well. Now, I want to hear from you. Here's a question to think about. In your own life, can you identify a moment where a small, random-seeming event led to enormous consequences? Write that down, think about it, and maybe share it with someone. I'm curious what you'll find.